Chapter 11 Transition to Complex Airplanes Introduction. A high-performance airplane is defined as an airplane with an engine capable of developing more than 200 horsepower. A complex airplane is an airplane that has a retractable landing gear, flaps, and a controllable pitch propeller. In lieu of a controllable pitch propeller, the aircraft could also have an engine control system consisting of a digital computer and associated accessories for controlling the engine and the propeller. A seaplane would still be considered complex if it meets the description above, except for having floats instead of a retractable landing gear system. Transition to a complex airplane, or a high-performance airplane, can be demanding for most pilots without previous experience. Increased performance and complexity both require additional planning, judgment, and piloting skills. Transition to these types of airplanes, therefore, should be accomplished in a systematic manner through a structured course of training administered by a qualified flight instructor. Airplanes can be designed to fly through a wide range of airspeeds. High-speed flight requires smaller wing areas and moderately cambered airfoils, whereas low-speed flight is obtained with airfoils with a greater camber and larger wing area. Figure 11.1. Many compromises are often made by designers to provide for higher speed cruise flight and low speeds for landing. Flaps are a common design effort to increase an airfoil's camber and the wing's surface area for lower speed flight. Figure 11.2. Since an airfoil cannot have two different cambers at the same time, one of two things must be done. Either the airfoil can be a compromise, or a cruise airfoil can be combined with a device for increasing the camber of the airfoil for low-speed flight. Camber is the asymmetry between the top and the bottom surfaces of an airfoil. One method for varying an airfoil's camber is the addition of trailing edge flaps. Engineers call these devices a high-lift system. Function of flaps. Flaps work primarily by changing the camber of the airfoil, which increases the wing's lift coefficient, and with some flap designs the surface area of the wing is also increased. Flap deflection does not increase the critical stall angle of attack, AOA, and, in some cases, flap deflection actually decreases the critical OA. Deflection of a wing's control surfaces, such as ailerons and flaps, alters both lift and drag. With aileron deflection, there is asymmetrical lift which imparts a rolling moment about the airplane's longitudinal axis. Wing flaps act symmetrically about the longitudinal axis, producing no rolling moment. However, both lift and drag increase, as well as a pitching moment about the lateral axis. Lift is a function of several variables including air density, velocity, surface area, and lift coefficient. Since flaps increase an airfoil's lift coefficient, lift is increased. Figure 11.3. As flaps are deflected, the aircraft may pitch nose up, nose down, or have minimal changes in pitch attitude. Pitching moment is caused by the rearward movement of the wing's center of pressure. However, that pitching behavior depends on several variables including flap type, wing position, downwash behavior, and horizontal tail location. Consequently, pitch behavior depends on the design features of the particular airplane. Flap deflection of up to 15 degrees primarily produces lift with minimal increases in drag. Deflection beyond 15 degrees produces a large increase in drag. Drag from flap deflection is parasite drag and, as such, is proportional to the square of the speed. Also, deflection beyond 15 degrees produces a significant nose-up pitching moment in most high-wing airplanes because the resulting downwash increases the airflow over the horizontal tail. Flap effectiveness. Flap effectiveness depends on a number of factors, but the most noticeable are size and type. For the purpose of this chapter, trailing edge flaps are classified as four basic types: plane, hinged, slit, slotted, and Fowler. Figure 11.4. The plane or hinge flap is a hinged section of the wing. The structure and function are comparable to the other control surfaces, ailerons, rudder, and elevator. The split flap is more complex. It is the lower or underside portion of the wing. Deflection of the flap leaves the upper trailing edge of the wing undisturbed. It is, however, more effective than the hinge flap because of greater lift and less pitching moment, but there is more drag. Split flaps are more useful for landing, but the partially deflected hinge flaps have the advantage in takeoff. The split flap has significant drag at small deflections, whereas the hinge flap does not because airflow remains attached to the flap. The slotted flap has a gap between the wing and the leading edge of the flap. The slot allows high-pressure airflow on the wing undersurface to energize the lower pressure over the top, thereby delaying flow separation. The slotted flap has greater lift than the hinge flap but less than the split flap, but, because of a higher lift-drag ratio, it gives better takeoff and climb performance. Small deflections of the slotted flap give a higher drag than the hinge flap but less than the split. This allows the slotted flap to be used for takeoff. The Fowler flap deflects down and aft to increase the wing area. This flap can be multi-slotted, making it the most complex of the trailing edge systems. This system does, however, give the maximum lift coefficient. Drag characteristics at small deflections are much like the slotted flap. Fowler flaps are most commonly used on larger airplanes because of their structural complexity and difficulty in sealing the slots. Operational procedures: it would be impossible to discuss all the many airplane design and flap combinations. This emphasizes the importance of the Federal Aviation Administration, FAA, approved Airplane Flight Manual and/or Pilot's Operating Handbook, AFM/PO, for a given airplane. While some AFM/POs are specific as to operational use of flaps, others leave the use of flaps to pilot discretion. Hence, flap operation makes pilot judgment of critical importance. Since flap operation is used for landings and takeoffs, during which the airplane is in close proximity to the ground where the margin for error is small. Since the recommendations given in the AFM/PO are based on the airplane and the flap design, the pilot must relate the manufacturer's recommendation to aerodynamic effects of flaps. This requires basic background knowledge of flap aerodynamics and geometry. With this information, a decision as to the degree of flap deflection and time of deflection based on runway and approach conditions relative to the wind conditions can be made. The time of flap extension and degree of deflection are related. Large flap deflections at one single point in the landing pattern produce large lift changes that require significant pitch and power changes in order to maintain airspeed and glide slope. Incremental deflection of flaps on downwind base and final approach allow smaller adjustment of pitch and power compared to extension of full flaps all at one time. This procedure facilitates a more stabilized approach. While all landings should be accomplished at the slowest speed possible for a given situation, a soft or short field landing requires minimal speed at touchdown, while a short field obstacle approach requires minimum speed and a steep approach angle. Flap extension, particularly beyond 30 degrees, results in significant levels of drag. As such, large angles of flap deployment require higher power settings than used with partial flaps. When steep approach angles in short fields combine with power to offset the drag produced by the flaps, the landing flare becomes critical. The drag produces a high sink rate that must be controlled with power, yet failure to reduce power at a rate so that the power is idle at touchdown allows the airplane to float down the runway. A reduction in power too early can result in a hard landing and damage or loss of control. Crosswind component is another factor to be considered in the degree of flap extension. The deflected flap presents a surface area for the wind to act on. With flaps extended in a crosswind, the wing on the upwind side is more affected than the downwind wing. The effect is reduced to a slight extent in the crabbed approach since the airplane is more nearly aligned with the wind. When using a wing-low approach, the lowered wing partially blocks the upwind flap. The dihedral of the wing combined with the flap and wind make lateral control more difficult. Lateral control becomes more difficult as flap extension reaches maximum and the crosswind becomes perpendicular to the runway. With flaps extended, the crosswind effects on the wing become more pronounced as the airplane comes closer to the ground. The wing, flap, and ground form a container that is filled with air by the crosswind. Since the flap is located behind the main landing gear, when the wind strikes the deflected flap and fuselage side, the upwind wing tends to rise and the airplane tends to turn into the wind. Proper control position is essential for maintaining runway alignment. Depending on the amount of crosswind, it may be necessary to retract the flaps soon after touchdown in order to maintain control of the airplane. The go-around is another factor to consider when making a decision about degree of flap deflection and about where in the landing pattern to extend flaps. Because of the nose-down pitching moment produced with flap extension, trim is used to offset this pitching moment. Application of full power in the go-around increases the airflow over the wing. This produces additional lift, causing significant changes in pitch. The pitch-up tendency does not diminish completely with flap retraction because of the trim setting. Expedient retraction of flaps is desirable to eliminate drag, however, the pilot must be prepared for rapid changes in pitch forces as the result of trim and the increase in airflow over the control surfaces. Figure 11.5. The degree of flap deflection combined with design configuration of the horizontal tail relative to the wing require carefully monitoring of pitch and airspeed, carefully control flap retraction to minimize altitude loss, and properly use the rudder for coordination. Considering these factors, it is good practice to extend the same degree of flap deflection at the same point in the landing pattern for each landing. This requires that a consistent traffic pattern be used. This allows for a pre-planned go-around sequence based on the airplane's position in the landing pattern. There is no single formula to determine the degree of flap deflection to be used on landing because a landing involves variables that are dependent on each other. The AFM/PO for the particular airplane contains the manufacturer's recommendations for some landing situations. On the other hand, AFM/PO information on flap usage for takeoff is more precise. The manufacturer's requirements are based on the climb performance produced by a given flap design. Under no circumstances should a flap setting given in the AFM/PO be exceeded for takeoff. Controllable pitch propeller fixed pitch propellers are designed for best efficiency at one speed of rotation and forward speed. This type of propeller provides suitable performance in a narrow range of airspeeds, however, efficiency would suffer considerably outside this range. To provide high propeller efficiency through a wide range of operation, the propeller blade angle must be controllable. The most effective way of controlling the propeller blade angle is by means of a constant speed governing system. Constant speed propeller. The constant speed propeller keeps the blade angle adjusted for maximum efficiency for most conditions of flight. The pilot controls the engine revolutions per minute, RPM, indirectly by means of a propeller control in the flight deck, which is connected to a propeller governor. For maximum takeoff power, the propeller control is moved all the way forward to the low pitch/high RPM position, and the throttle is moved forward to the maximum allowable manifold pressure position. Figure 11.6. To reduce power for climb or cruise, manifold pressure is reduced to the desired value with the throttle, and the engine RPM is reduced by moving the propeller control back toward the high pitch/low RPM position until the desired RPM is observed on the tachometer. Pulling back on the propeller control causes the propeller blades to move to a higher angle. Increasing the propeller blade angle of attack results in an increase in the resistance of the air. This puts a load on the engine so it slows down. In other words, the resistance of the air at the higher blade angle is greater than the torque, or power, delivered to the propeller by the engine, so it slows down to a point where forces are in balance. When an aircraft engine is running at constant speed, the torque, power, exerted by the engine at the propeller shaft must equal the opposing load provided by the resistance of the air. The RPM is controlled by regulating the torque absorbed by the propeller, in other words by increasing or decreasing the resistance offered by the air to the propeller. This is accomplished with a constant speed propeller by means of a governor. The governor, in most cases, is geared to the engine crankshaft and thus is sensitive to changes in engine RPM. When an airplane is nosed up into a climb from level flight, the engine tends to slow down. Since the governor is sensitive to small changes in engine RPM, it decreases the blade angle just enough to keep the engine speed from falling off. If the airplane is nose down into a dive, the governor increases the blade angle enough to prevent the engine from overspeeding. This allows the engine to maintain a constant RPM, thereby maintaining the power output. Changes in airspeed and power can be obtained by changing RPM at a constant manifold pressure, by changing the manifold pressure at a constant RPM, or by changing both RPM and manifold pressure. The constant speed propeller makes it possible to obtain an infinite number of power settings. Takeoff, climb, and cruise. During takeoff, when the forward motion of the airplane is at low speeds and when maximum power and thrust are required, the constant speed propeller sets up a low propeller blade angle, pitch. The low blade angle keeps the OA, with respect to the relative wind, small and efficient at the low speed. Figure 11.7. At the same time, it allows the propeller to handle a smaller mass of air per revolution. This light load allows the engine to turn at maximum RPM and develop maximum power. Although the mass of air per revolution is small, the number of RPM is high. Thrust is maximum at the beginning of the takeoff and then decreases as the airplane gains speed and the airplane drag increases. Due to the high slipstream velocity during takeoff, the effective lift of the wing behind the propellers is increased. As the airspeed increases after liftoff, the load on the engine is lightened because of the small blade angle. The governor senses this and increases the blade angle slightly. Again, the higher blade angle, with the higher speeds, keeps the OA with respect to the relative wind small and efficient. For climb after takeoff, the power output of the engine is reduced to climb power by decreasing the manifold pressure and lowering RPM by increasing the blade angle. At the higher climb airspeed and the higher blade angle, the propeller is handling a greater mass of air per second at a lower slipstream velocity. This reduction in power is offset by the increase in propeller efficiency. The OA is again kept small by the increase in the blade angle with an increase in airspeed. At cruising altitude, when the airplane is in level flight, less power is required to produce a higher airspeed than is used in climb. Consequently, engine power is again reduced by lowering the manifold pressure and increasing the blade angle, to decrease RPM. The higher airspeed and higher blade angle enable the propeller to handle a still greater mass of air per second at still smaller slipstream velocity. At normal cruising speeds, propeller efficiency is at or near maximum efficiency. Blade angle control. Once the RPM settings for the propeller are selected, the propeller governor automatically adjusts the blade angle to maintain the selected RPM. It does this by using oil pressure. Generally, the oil pressure used for pitch change comes directly from the engine lubricating system. When a governor is employed, engine oil is used and the oil pressure is usually boosted by a pump that is integrated with the governor. The higher pressure provides a quicker blade angle change. The RPM at which the propeller is to operate is adjusted in the governor head. The pilot changes this setting by changing the position of the governor rack through the flight deck propeller control. On some constant speed propellers, changes in pitch are obtained by the use of an inherent centrifugal twisting moment of the blades that tends to flatten the blades toward low pitch and oil pressure applied to a hydraulic piston connected to the propeller blades, which moves them toward high pitch. Another type of constant speed propeller uses counterweights attached to the blade shanks in the hub. Governor oil pressure and the blade twisting moment move the blades toward the low pitch position, and centrifugal force acting on the counterweights moves them, and the blades, toward the high pitch position. In the first case above, governor oil pressure moves the blades towards high pitch, and in the second case, governor oil pressure and the blade twisting moment move the blades toward low pitch. A loss of governor oil pressure, therefore, affects each differently. Governing range. The blade angle range for constant speed propellers varies from about 111/2 of a degree to 40 degrees. The higher the speed of the airplane, the greater the blade angle range. Figure 11.8, the range of possible blade angles is termed the propeller's governing range. The governing range is defined by the limits of the propeller blade's travel between high and low blade angle pitch stops. As long as the propeller blade angle is within the governing range and not against either pitch stop, a constant engine RPM is maintained. However, once the propeller blade reaches its pitch stop limit, the engine RPM increases or decreases with changes in airspeed and propeller load similar to a fixed pitch propeller. For example, once a specific RPM is selected, if the airspeed decreases enough, the propeller blades reduce pitch in an attempt to maintain the selected RPM until they contact their low pitch stops. From that point, any further reduction in airspeed causes the engine RPM to decrease. Conversely, if the airspeed increases, the propeller blade angle increases until the high pitch stop is reached. The engine RPM then begins to increase. Constant speed propeller operation. The engine is started with the propeller control in the low pitch/high RPM position. This position reduces the load or drag of the propeller, and the result is easier starting and warm-up of the engine. During warm-up, the propeller blade changing mechanism is operated slowly and smoothly through a full cycle. This is done by moving the propeller control, with the manifold pressure set to produce about 1,600 revolutions per minute, to the high pitch/low RPM position, allowing the RPM to stabilize, and then moving the propeller control back to the low pitch takeoff position. This is done for two reasons: to determine whether the system is operating correctly and to circulate fresh warm oil through the propeller governor system. Remember, the oil has been trapped in the propeller cylinder since the last time the engine was shut down. There is a certain amount of leakage from the propeller cylinder, and the oil tends to congeal, especially if the outside air temperature is low. Consequently, if the propeller is not exercised before takeoff, there is a possibility that the engine may overspeed on takeoff. An airplane equipped with a constant speed propeller has better takeoff performance than a similarly powered airplane equipped with a fixed pitch propeller. This is because with a constant speed propeller, an airplane can develop its maximum rated horsepower, red line on the tachometer, while motionless. An airplane with a fixed pitch propeller, on the other hand, must accelerate down the runway to increase airspeed and aerodynamically unload the propeller so that RPM and horsepower can steadily build up to their maximum. With a constant speed propeller, the tachometer reading should come up to within 40 revolutions per minute of the red line as soon as full power is applied and remain there for the entire takeoff. Excessive manifold pressure raises the cylinder combustion pressures, resulting in high stresses within the engine. Excessive pressure also produces high engine temperatures. A combination of high manifold pressure and low RPM can induce damaging detonation. In order to avoid these situations, the following sequence should be followed when making power changes. When increasing power, increase the RPM first and then the manifold pressure. When decreasing power, Decrease the manifold pressure first and then decrease the RPM. The cruise power charts in the AFM/PO should be consulted when selecting cruise power settings. Whatever the combinations of RPM and manifold pressure listed in these charts, they have been flight tested and approved by engineers for the respective airframe and engine manufacturer. Therefore, if there are power settings, such as 2100 revolutions per minute and 24 inches manifold pressure in the power chart, they are approved for use. With a constant speed propeller, a power descent can be made without overspeeding the engine. The system compensates for the increased airspeed of the descent by increasing the propeller blade angles. If the descent is too rapid or is being made from a high altitude, the maximum blade angle limit of the blades is not sufficient to hold the RPM constant. When this occurs, the RPM is responsive to any change in throttle setting. Although the governor responds quickly to any change in throttle setting, a sudden and large increase in the throttle setting causes a momentary overspeeding of the engine until the blades become adjusted to absorb the increased power. If an emergency demanding full power should arise during approach, the sudden advancing of the throttle causes momentary overspeeding of the engine beyond the RPM for which the governor is adjusted. Some important points to remember concerning constant speed propeller operation are: the red line on the tachometer not only indicates maximum allowable RPM, it also indicates the RPM required to obtain the engine's rated horsepower. A momentary propeller overspeed may occur when the throttle is advanced rapidly for takeoff. This is usually not serious if the rated RPM is not exceeded by 10% for more than 3 seconds. The green arc on the tachometer indicates the normal operating range. When developing power in this range, the engine drives the propeller. Below the green arc, however, it is usually the windmilling propeller that powers the engine. Prolonged operation below the green arc can be detrimental to the engine. On takeoffs from low elevation airports, the manifold pressure in inches of mercury may exceed the RPM. This is normal in most cases, but the pilot should always consult the AFM/PO for limitations. All power changes should be made smoothly and slowly to avoid overboosting and/or overspeeding. Turbocharging. The turbocharged engine allows the pilot to maintain sufficient cruise power at high altitudes where there is less drag, which means faster true air speeds and increased range with fuel economy. At the same time, the power plant has flexibility and can be flown at a low altitude without the increased fuel consumption of a turbine engine. When attached to the standard power plant, the turbocharger does not take any horsepower from the engine to operate. It is relatively simple mechanically, and some models can pressurize the cabin as well. The turbocharger is an exhaust-driven device that raises the pressure and density of the induction air delivered to the engine. It consists of 2 separate components, a compressor and a turbine connected by a common shaft. The compressor supplies pressurized air to the engine for high-altitude operation. The compressor and its housing are between the ambient air intake and the induction air manifold. The turbine and its housing are part of the exhaust system and utilize the flow of exhaust gases to drive the compressor. Figure 11.9, the turbine has the capability of producing manifold pressure in excess of the maximum allowable for the particular engine. In order not to exceed the maximum allowable manifold pressure, a bypass or waste gate is used so that some of the exhaust is diverted overboard before it passes through the turbine. The position of the waste gate regulates the output of the turbine and therefore, the compressed air available to the engine. When the waste gate is closed, all of the exhaust gases pass through and drive the turbine. As the waste gate opens, some of the exhaust gases are routed around the turbine through the exhaust bypass and overboard through the exhaust pipe. The wastegate actuator is a spring-loaded piston operated by engine oil pressure. The actuator, which adjusts the wastegate position, is connected to the wastegate by a mechanical linkage. The control center of the turbocharger system is the pressure controller. This device simplifies turbocharging to one control, the throttle. Once the desired manifold pressure is set, virtually no throttle adjustment is required with changes in altitude. The controller senses compressor discharge requirements for various altitudes and controls the oil pressure to the wastegate actuator, which adjusts the wastegate accordingly. Thus the turbocharger maintains only the manifold pressure called for by the throttle setting. Ground boosting versus altitude turbocharging. Altitude turbocharging, sometimes called normalizing, is accomplished by using a turbocharger that maintains maximum allowable sea level manifold pressure, normally 29 to 30 Hg, up to a certain altitude. This altitude is specified by the airplane manufacturer and is referred to as the airplane's critical altitude. Above the critical altitude, the manifold pressure decreases as additional altitude is gained. Ground boosting, on the other hand, is an application of turbocharging where more than the standard 29 inches of manifold pressure is used in flight. In various airplanes using ground boosting, takeoff manifold pressures may go as high as 45 Hg. Although a sea-level power setting and maximum RPM can be maintained up to the critical altitude, this does not mean that the engine is developing sea-level power. Engine power is not determined just by manifold pressure and RPM. Induction air temperature is also a factor. Turbocharged induction air is heated by compression. This temperature rise decreases induction air density, which causes a power loss. Maintaining the equivalent horsepower output requires a somewhat higher manifold pressure at a given altitude than if the induction air were not compressed by turbocharging. If, on the other hand, the system incorporates an automatic density controller which, instead of maintaining a constant manifold pressure, automatically positions the wastegate so as to maintain constant air density to the engine, a near constant horsepower output results. Operating characteristics. First and foremost, all movements of the power controls on turbocharged engines should be slow and smooth. Aggressive and/or abrupt throttle movements increase the possibility of overboosting. Carefully monitor engine indications when making power changes. When the wastegate is open, the turbocharged engine reacts the same as a normally aspirated engine when the RPM is varied. That is, when the RPM is increased, the manifold pressure decreases slightly. When the engine RPM is decreased, the manifold pressure increases slightly. However, when the wastegate is closed, manifold pressure variation with engine RPM is just the opposite of the normally aspirated engine. An increase in engine RPM results in an increase in manifold pressure, and a decrease in engine RPM results in a decrease in manifold pressure. Above the critical altitude, where the wastegate is closed, any change in airspeed results in a corresponding change in manifold pressure. This is true because the increase in ram air pressure with an increase in airspeed is magnified by the compressor, resulting in an increase in manifold pressure. The increase in manifold pressure creates a higher mass flow through the engine, causing higher turbine speeds and thus further increasing manifold pressure. When running at high altitudes, aviation gasoline may tend to vaporize prior to reaching the cylinder. If this occurs in the portion of the fuel system between the fuel tank and the engine-driven fuel pump, an auxiliary positive pressure pump may be needed in the tank. Since engine-driven pumps pull fuel, they are easily vapor-locked. A boost pump provides positive pressure, pushes the fuel, reducing the tendency to vaporize. Heat management. Turbocharged engines must be thoughtfully and carefully operated with continuous monitoring of pressures and temperatures. There are two temperatures that are especially important: turbine inlet temperature, TIT, or, in some installations, exhaust gas temperature, EGT, and cylinder head temperature. TIT or EGT limits are set to protect the elements in the hot section of the turbocharger, while cylinder head temperature limits protect the engine's internal parts. Due to the heat of compression of the induction air, a turbocharged engine runs at higher operating temperatures than a non-turbocharged engine. Because turbocharged engines operate at high altitudes, their environment is less efficient for cooling. At altitude, the air is less dense and, therefore, cools less efficiently. Also, the less dense air causes the compressor to work harder. Compressor turbine speeds can reach 80,000 to 100,000 revolutions per minute, adding to the overall engine operating temperatures. Turbocharged engines are also operated at higher power settings a greater portion of the time. High heat is detrimental to piston engine operation. Its cumulative effects can lead to piston, ring, and cylinder head failure and place thermal stress on other operating components. Excessive cylinder head temperature can lead to detonation, which in turn can cause catastrophic engine failure. Turbocharged engines are especially heat sensitive. The key to turbocharger operation is effective heat management. Monitor the condition of a turbocharged engine with manifold pressure gauge, tachometer, exhaust gas temperature/turbine inlet temperature gauge, and cylinder head temperature. Manage the heat system with the throttle, propeller RPM, mixture, and cowl flaps. At any given cruise power, the mixture is the most influential control over the exhaust gas/TIT. The throttle regulates total fuel flow, but the mixture governs the fuel-to-air ratio. The mixture, therefore, controls temperature. Exceeding temperature limits in and after takeoff climb is usually not a problem since a full rich mixture cools with excess fuel. At cruise, power is normally reduced and mixture adjusted accordingly. Under cruise conditions, monitor temperature limits closely because that is when the temperatures are most likely to reach the maximum, even though the engine is producing less power. Overheating in an en route climb, however, may require fully open cowl flaps and a higher airspeed. Since turbocharged engines operate hotter at altitude than do normally aspirated engines, they are more prone to damage from cooling stress. Gradual reductions in power and careful monitoring of temperatures are essential in the descent phase. Extending the landing gear during the descent may help control the airspeed while maintaining a higher engine power setting. This allows the pilot to reduce power in small increments, which allows the engine to cool slowly. It may also be necessary to lean the mixture slightly to eliminate roughness at the lower power settings. Turbocharger failure. Because of the high temperatures and pressures produced in the turbine exhaust systems, any malfunction of the turbocharger must be treated with extreme caution. In all cases of turbocharger operation, the manufacturer's recommended procedures should be followed. This is especially so in the case of turbocharger malfunction. However, in those instances where the manufacturer's procedures do not adequately describe the actions to be taken in the event of a turbocharger failure, the following procedures should be used. Overboost condition. If an excessive rise in manifold pressure occurs during normal advancement of the throttle, possibly owing to faulty operation of the wastegate, immediately retard the throttle smoothly to limit the manifold pressure below the maximum for the RPM and mixture setting. Operate the engine in such a manner as to avoid a further overboost condition. Low manifold pressure. Although this condition may be caused by a minor fault, it is quite possible that a serious exhaust leak has occurred, creating a potentially hazardous situation. Shut down the engine in accordance with the recommended engine failure procedures, unless a greater emergency exists that warrants continued engine operation. If continuing to operate the engine, use the lowest power setting demanded by the situation and land as soon as practicable. It is very important to ensure that corrective maintenance is undertaken following any turbocharger malfunction. Retractable landing gear. The primary benefits of being able to retract the landing gear are increased climb performance and higher cruise airspeeds due to the resulting decrease in drag. Retractable landing gear systems may be operated either hydraulically or electrically, or may employ a combination of the two systems. Warning indicators are provided in the flight deck to show the pilot when the wheels are down and locked, and when they are up and locked, or if they are in intermediate positions. Systems for emergency operation are also provided. The complexity of the retractable landing gear system requires that specific operating procedures be adhered to and that certain operating limitations not be exceeded. Landing gear systems. An electrical landing gear retraction system utilizes an electrically driven motor for gear operation. The system is basically an electrically driven jack for raising and lowering the gear. When a switch in the flight deck is moved to the up position, the electric motor operates. Through a system of shafts, gears, adapters, an actuator screw, and a torque tube, a force is transmitted to the drag strut linkages. Thus, the gear retracts and locks. Struts are also activated that open and close the gear doors. If the switch is moved to the down position, the motor reverses and the gear moves down and locks. Once activated, the gear motor continues to operate until an up or down limit switch on the motor's gearbox is tripped. A hydraulic landing gear retraction system utilizes pressurized hydraulic fluid to actuate linkages to raise and lower the gear. When a switch in the flight deck is moved to the up position, hydraulic fluid is directed into the gear up line. The fluid flows through sequenced valves and down locks to the gear actuating cylinders. A similar process occurs during gear extension. The pump that pressurizes the fluid in the system can be either engine-driven or electrically powered. If an electrically powered pump is used to pressurize the fluid, the system is referred to as an electrohydraulic system. The system also incorporates a hydraulic reservoir to contain excess fluid and to provide a means of determining system fluid level. Regardless of its power source, the hydraulic pump is designed to operate within a specific range. When a sensor detects excessive pressure, a relief valve within the pump opens, and hydraulic pressure is routed back to the reservoir. Another type of relief valve prevents excessive pressure that may result from thermal expansion. Hydraulic pressure is also regulated by limit switches. Each gear has two limit switches, one dedicated to extension and one dedicated to retraction. These switches de-energize the hydraulic pump after the landing gear has completed its gear cycle. In the event of limit switch failure, a backup pressure relief valve activates to relieve excess system pressure. Controls and position indicators. Landing gear position is controlled by a switch on the flight deck panel. In most airplanes, the gear switch is shaped like a wheel in order to facilitate positive identification and to differentiate it from other flight deck controls. Landing gear position indicators vary with different make and model airplanes. However, the most common types of landing gear position indicators utilize a group of lights. One type consists of a group of 3 green lights, which illuminate when the landing gear is down and locked. Figure 11.10, Another type consists of one green light to indicate when the landing gear is down and an amber light to indicate when the gear is up. Figure 1111, still other systems incorporate a red or amber light to indicate when the gear is in transit or unsafe for landing. Figure 1112, the lights are usually of the press to test type, and the bulbs are interchangeable. Figure 1110, other types of landing gear position indicators consist of tab type indicators with markings up to indicate the gear is up and locked, a display of red and white diagonal stripes to show when the gear is unlocked, or a silhouette of each gear to indicate when it locks in the down position. Landing gear safety devices. Most airplanes with a retractable landing gear have a gear warning horn that sounds when the airplane is configured for landing and the landing gear is not down and locked. Normally, the horn is linked to the throttle or flap position and/or the airspeed indicator so that when the airplane is below a certain airspeed, configuration, or power setting with the gear retracted, the warning horn sounds. Accidental retraction of a landing gear may be prevented by such devices as mechanical down locks, safety switches, and ground locks. Mechanical down locks are built-in components of a gear retraction system and are operated automatically by the gear retraction system. To prevent accidental operation of the down locks and inadvertent landing gear retraction while the airplane is on the ground, electrically operated safety switches are installed. A landing gear safety switch, sometimes referred to as a squat switch, is usually mounted in a bracket on one of the main gear shock struts. Figure 1112, when the strut is compressed by the weight of the airplane, the switch opens the electrical circuit to the motor or mechanism that powers retraction. In this way, if the landing gear switch in the flight deck is placed in the retract position when weight is on the gear remains extended, and the warning horn may sound as an alert to the unsafe condition. Once the weight is off the gear, however, such as on takeoff, the safety switch releases and the gear retracts. Many airplanes are equipped with additional safety devices to prevent collapse of the gear when the airplane is on the ground. These devices are called ground locks. One common type is a pin installed in aligned holes drilled in 2 or more units of the landing gear support structure. Another type is a spring-loaded clip designed to fit around and hold 2 or more units of the support structure together. All types of ground locks usually have red streamers permanently attached to them to readily indicate whether or not they are installed. Emergency gear extension systems. The emergency extension system lowers the landing gear if the main power system fails. Some airplanes have an emergency release handle in the flight deck, which is connected through a mechanical linkage to the gear up locks. When the handle is operated, it releases the up locks and allows the gear to free fall or extend under their own weight. Figure 1113, on other airplanes, release of the up lock is accomplished using compressed gas, which is directed to up lock release cylinders. In some airplanes, design configurations make emergency extension of the landing gear by gravity and air loads alone impossible or impractical. In these airplanes, provisions are included for forceful gear extension in an emergency. Some installations are designed so that either hydraulic fluid or compressed gas provides the necessary pressure, while others use a manual system, such as a hand crank for emergency gear extension. Figure 1114, hydraulic pressure for emergency operation of the landing gear may be provided by an auxiliary hand pump, an accumulator, or an electrically powered hydraulic pump depending on the design of the airplane. Operational procedures pre-flight. Because of their complexity, retractable landing gear demands a close inspection prior to every flight. The inspection should begin inside the flight deck. First, make certain that the landing gear selector switch is in the gear down position. Then, turn on the battery master switch and ensure that the landing gear position indicators show that the gear is down and locked. External inspection of the landing gear consists of checking individual system components. Figure 1114, the landing gear and adjacent areas should be clean and free of mud and debris. Dirty switches and valves may cause false safe light indications or interrupt the extension cycle before the landing gear is completely down and locked. The wheel well should be clear of any obstructions, as foreign objects may damage the gear or interfere with its operation. Bent gear doors may be an indication of possible problems with normal gear operation. Ensure shock struts are properly inflated and that the pistons are clean. Check main gear and nose gear up lock and down lock mechanisms for general condition. Power sources and retracting mechanisms are checked for general condition, obvious defects, and security of attachment. Check hydraulic lines for signs of chafing and leakage at attach points. Warning system micro switches, squat switches, are checked for cleanliness and security of attachment. Actuating cylinders, sprockets, universal joints, drive gears, linkages, and any other accessible components are checked for condition and obvious defects. The airplane structure to which the landing gear is attached is checked for distortion, cracks, and general condition. All bolts and rivets should be intact and secure. Takeoff and climb. Normally, the landing gear is retracted after liftoff when the airplane has reached an altitude where, in the event of an engine failure or other emergency requiring an aborted takeoff. Figure 1113. Typical emergency gear extension systems. Figure 1114. Retractable landing gear inspection checkpoints. The airplane could no longer be landed on the runway. This procedure, however, may not apply to all situations. Pre-planned landing gear retraction taking into account the following: length of the runway, climb gradient, obstacle clearance requirements, the characteristics of the terrain beyond the departure end of the runway, the climb characteristics of the particular airplane. For example, in some situations it may be preferable, in the event of an engine failure, to make an off-airport forced landing with the gear extended in order to take advantage of the energy-absorbing qualities of the terrain. See Chapter 19, Emergency Procedures. In which case, a delay in retracting the landing gear after takeoff from a short runway may be warranted. In other situations, obstacles in the climb path may warrant a timely gear retraction after takeoff. Also, in some airplanes the initial climb pitch attitude is such that any view of the runway remaining is blocked, making an assessment of the feasibility of touching down on the remaining runway difficult. Avoid premature landing gear retraction and do not retract the landing gear until a positive rate of climb is indicated on the flight instruments. If the airplane has not attained a positive rate of climb, there is always the chance it may settle back onto the runway with the gear retracted. This is especially so in cases of premature liftoff. Remember that leaning forward to reach the landing gear selector may result in inadvertent forward pressure on the yoke, which causes the airplane to descend. As the landing gear retracts, airspeed increases and the airplane's pitch attitude may change. The gear may take several seconds to retract. Gear retraction and locking, and gear extension and locking, is accompanied by sound and feel that are unique to the specific make and model airplane. Become familiar with the sound and feel of normal gear retraction so that any abnormal gear operation can be readily recognized. Abnormal landing gear retraction is most often a clear sign that the gear extension cycle will also be abnormal. Approach and landing. The operating loads placed on the landing gear at higher airspeeds may cause structural damage due to the forces of the airstream. Limiting speeds, therefore, are established for gear operation to protect the gear components from becoming overstressed during flight. These speeds may not be found on the airspeed indicator. They are published in the AFM/PO for the particular airplane, and are usually listed on placards in the flight deck. Figure 1115, the maximum landing extended speed, VLE, is the maximum speed at which the airplane can be flown with the landing gear extended. The maximum landing gear operating speed, VLO, is the maximum speed at which the landing gear may be operated through its cycle. The landing gear is extended by placing the gear selector switch in the gear down position. As the landing gear extends, the airspeed decreases and the pitch attitude may change. During the several seconds it takes for the gear to extend, be attentive to any abnormal sounds or feel. Confirm that the landing gear has extended and locked by the normal sound and feel of the system operation, as well as by the gear position indicators in the flight deck. Unless the landing gear has been previously extended to aid in a descent to traffic pattern altitude, the landing gear should be extended by the time the airplane reaches a point on the downwind leg that is opposite the point of intended landing. Establish a standard procedure consisting of a specific position on the downwind leg at which to lower the landing gear. Strict adherence to this procedure aids in avoiding unintentional gear-up landings. Operation of an airplane equipped with a retractable landing gear requires the deliberate, careful, and continued use of an appropriate checklist. When on the downwind leg, make it a habit to complete the before landing checklist for that airplane. This accomplishes two purposes. It ensures that action has been taken to lower the gear and establishes awareness so that the gear down indicators can be rechecked prior to landing. Unless good operating practices dictate otherwise, the landing rolls should be completed and the airplane should be clear of the runway before any levers or switches are operated. This technique greatly reduces the chance of inadvertently retracting the landing gear while on the ground. Wait until after rollout and clearing the runway to focus attention on the after-landing checklist. This practice allows for positive identification of the proper controls. When transitioning to retractable gear airplanes, it is important to consider some frequent pilot errors. These include pilots that have neglected to extend landing gear, inadvertently retracted landing gear, activated gear but failed to check gear position, misused emergency gear system, retracted gear prematurely on takeoff, Extended gear too late. These mistakes are not only committed by pilots who have just transitioned to complex aircraft, but also by pilots who have developed a sense of complacency over time. In order to minimize the chances of a landing gear-related mishap, use an appropriate checklist. A condensed checklist mounted in view is a reminder for its use, and easy reference can be especially helpful. Be familiar with, and periodically review, the landing gear emergency extension procedures for the particular airplane. Be familiar with the landing gear warning horn and warning light systems for the particular airplane. Use the horn system to cross-check the warning light system when an unsafe condition is noted. Review the procedure for replacing light bulbs in the landing gear warning light displays for the particular airplane, so that you can properly replace a bulb to determine if the bulbs in the display is good. Check to see if spare bulbs are available in the airplane spare bulb supply as part of a pre-flight inspection. Be familiar with and aware of the sounds and feel of a properly operating landing gear system. Transition training. Transition to a complex airplane or a high-performance airplane should be accomplished through a structured course of training administered by a competent and qualified flight instructor. The training should be accomplished in accordance with a ground and flight training syllabus. Figure 1116, this sample syllabus for transition training is an example. The arrangement of the subject matter may be changed, and the emphasis shifted to fit the qualifications of the transitioning pilot, the airplane involved, and the circumstances of the training situation. The goal is to ensure proficiency standards are achieved. These standards are contained in the Practical Test Standards, PTS, or Airman Certification Standard, ACS, as appropriate for the certificate that the transitioning pilot holds or is working towards. The training times indicated in the syllabus are for illustration purposes. Actual times must be based on the capabilities of the pilot. The time periods may be minimal for pilots with higher qualifications or increased for pilots who do not meet certification requirements or have had little recent flight experience. Chapter summary. Flying a complex or high-performance airplane requires a pilot to further divide his or her attention during the most critical phases of flight, takeoff and landing. The knowledge, judgment, and piloting skills required to fly these airplanes must be developed. It is essential that adequate training is received to ensure a complete understanding of the systems, their operation, both normal and emergency, and operating limitations.